Welcome everyone to a session on automata theory and computability. In today's session, let us learn the concept of minimization of DFSM. Okay, so why it is required to minimize a solved DFSM for a given problem? The answer is, see, for a given regular language, uh, I can have a multiple DFSM. I can have a multiple design, and some of the design may not be optimal, right? I may have a more number of states than actually required. So what we can do is we can follow this concept of minimizing a DFSM, where I get a very simple, less complex DFSM. Okay, so I get a DFSM with the less number of states, and the lesser the number of states, the simpler the DFSM, right? And and it becomes more easy to implement such design. Okay, and there are multiple ways of performing this task, that is a minimization of DFSM, and we'll follow one. Okay, and it is whatever we follow in this session need not be the only solution as a minimization of DFSM. In different textbook in by different authors, you can find a different solution. Okay, let us solve this problem, given problem, and try to minimize this DFSM. So initially we have to follow multiple steps. Initially what we need to do is we need to create classes. Okay, classes in the sense it's a set containing a group of states. Okay, and initially I'll be having two sets or two classes, class containing all the accepting state together, and a class that contains all the non-accepting states together. Okay, so initially the content of classes will be equal to a set containing two groups. Okay, so what are the accepting states here? I have 2 and 4, so I'll put them in a same class. Okay, and one more class is the rest of the states, those are non-accepting. So I have 1, 3, 5 and 6. Okay, so this is about the initial step, that is creating classes which contains a group of accepting states and a group of non-accepting states. And in the next further steps, what we do is we check, or we try to split this classes into multiple classes, and the following steps need to be iterated multiple times until certain condition is true. Okay, so we'll see that in the solution itself, directly in the solution. So step 1, what I will do is I'll check whether these classes, okay, these classes can be further splitted or not. Okay, so first let me take 2 and 4. Okay, so how to do? There are two. What are the various alphabet symbols? We have A and B, right? So first let me check for A. Okay. So what I do is I'll consider each and every state in my class. So first let me take a class of accepting states. I have 2 and 4, right? So 2 upon A. So where does the transition occur? Transition occurs to, see, 2 upon A will make a transition to 3, isn't it? And 3 belongs to a class of 1, 3, 5, 6. So I need to write 2 upon A will make a transition to a set or a class that contains 3. Okay, so I'll write in this way. Yes, so this is for 2 on A. Similarly, I need to write for 4 on A, because 2 and 4 come in the same class, right? Okay, 4 upon A, 4 upon A makes a transition to 6, and 6 belongs to a class containing 1, 3, 5, 6 again. So I will write that entire class that contains 6 in it. Okay, yeah. Okay, so for A, so if you observe, 2 upon A will make a transition to a class represented by 1356, and 4 upon A will also make a transition to a class containing 1356. So, since both 2 and A, 2 and 4 for the input symbol A will make a transition to the same set of class, that is 1356, there is no splitting required. Okay, there is no splitting required, but we are not done with the B, isn't it? So, let us check for B. 2 upon B. 2 upon B will make a transition to 6. So, I have to write the transition the same way as I have written for A. Okay. So, 6 belongs to 1, 3, 5, 6. Similarly, 4 upon B. So, 4 upon B will make a transition to 6. Okay. So, 4 also make a transition to 6. So, I have to write 1, 3, 5. So, what does this indicate? This indicates that uh, upon A and B, so 2 and 4 will make a transition to the same set, isn't it? Okay. So, first we have considered A. So, since 2 upon A made a transition to 1356 and 4 upon A made a transition to 1356, there is no splitting required. Okay, no splitting. And similarly here 2 upon B and 4 upon B will make a transition to the same class. So, no splitting required. So, at the end of one iteration, at the end of step 1, 4 and A will remain intact in the same class. Okay. Okay. Now, in step 1 itself, we have to check for 1, 3 and 1, 3, 5 and 6, right? We have to check for 1, 3, 5 and 6. We need to check whether 1, 3, 5 and 6 will be further splitted or not. Okay. So, we will see that. So, first let us check for A. Okay. So, let us start with 1. 1 upon A. So, 1 upon A will make a transition to 2, right? So, I have to write in this way, and 2 belong to a class containing 2 and 4. So, I have to write a transition in this way. Okay. Next, we have 3 upon A. So, 3 upon A will make a transition to 2. So, 2 again belongs to 2 comma 4. So, I have to write that entire set. Then comes 5. 5 upon A will make a transition to 2 itself. 2 belongs to a class containing 2 comma 4. Finally, I have 6, and 6 upon A will make a transition to 6, right? I have a self loop upon A. I have a self loop to 6, and 6 belongs to a class containing 1, 3, 5, 6, right? So, I have to write 1, 3, 5, 6. Okay. So, is the splitting required? Yes, the splitting is required in this case, because see, upon 1, 3 and 5 it makes a transition to the same set, that is 2 and 4, right? So, this will be together, further they will be together, but it is very clearly evident that 6 upon A will make a transition to a different set, that is a set containing 1, 3, 5 and 6. So, 6 at the end of this iteration, 6 will be further splitted from a class containing 1, 3, 5 and 6. Okay. So, 6 will go out, it will be separated, but we have to still check whether there is a further split or not. Okay. So, that is done by looking into B also, because we have simply saw upon A, right. So, we have to look into B. So, 1 upon B. So, where does the transition occur? The transition occurred to 4. So, 4 belongs to 2 comma 4. Okay. So, then comes 3 upon A, 3 upon B. So, this will make a transition to 3 upon A will make a transition to 2, that is again belongs to the same set containing 2 comma 4. Then I have 5 comma or 5 upon B. 5 upon B will make a transition to 4. Okay, will make transition to the same set. And finally 6 upon B. 6 upon B will make a transition to 6 itself. So that belongs to 1, 3, 5, 6. Okay. So even with respect to B, yeah, 6 is different, but that doesn't matter because 6 will be splitted anyways, because upon A, 6 upon A had made a different transition from that of a 1, 3 and 5, right? So 6 will be splitted for sure. And for B, upon B, as you can see, among 1, 3 and 5, it had made a transition to the same set, that is 2, 4, right? So there is no further splitting. So suppose 1 upon B had made a transition to 1, 3, 5, 6, then there would be a further split among 1, 3 and 5, right? But since it made a transition to the same set, that is 2 and 2, 4, there is no further splitting, right? So I can make a small note here: splitting required. Okay, splitting required. So at the end of step 1, what do I get? At the end of step 1, I'll get a new class. I get a class containing a new set. Okay, so let me write that. So the content of classes at the end of step 1 will be 2, 4 will be together because there was no split. Then 1, 3 and 5 remains together and 6 comes out, right? So 6 was separated from the set of, or from the class of 1, 3, 5 and 6, because it made a transition to the different class compared to the 1, 3 and 5, right? So this is the value of classes after step 1. Okay, so at the end of step 1, the content of classes has changed, right? Because there was a split that appeared in step 1. Now the contents are 2, 4, 1, 3, 5 and 6, since 6 got separated from 1, 3, 5 in step 1. So do we need to continue with the step 2? Yes, we need to continue with step 2 because there was a split in step 1. So we need to continue this iteration until we encounter no further splitting. Okay, so we have to follow the same procedure as we followed in step 1. Okay, so let us see 2 upon A. 2 upon A will make a transition to 3, which belongs to a set containing 1, 3 and 5. And 4 upon A will make a transition to 6, which is a different class, right? So the question is the splitting required? Yes, the splitting is required because the transition for A upon 2 and 4 had made a split, made a transition to 2 different classes, right? So split is required. Split required. Now to complete the procedure, we'll check for B. Okay. Now is it necessary to will transition upon B, will it make any difference? Actually the answer is no, because upon A 2 and 4 will be splitted for sure, and there cannot be a further split among 2 and 4 are two individual, it contains a single value, right? So there will not be a further split, but for the procedure let us see what happens for B, right? So 2 upon B will make a transition to 6, and 4 upon B will make a transition to 5, which belongs to 1, 3 and 5. Of course the split is required. Anyways the split would have been would be required upon A itself, but this will not make a difference actually, right? Because we would have splitted 2 and 4 upon A itself. Okay, so 2 and 4 at the end of this iteration, the entire step 2 iteration will be separated. Okay, so we did not come to the end of this iteration because we are yet to see for 1, 3 and 5, right? So let us see for that. For time being 2 and 4 are together, we'll split that at the end of this iteration. Now 1, 3, 4 upon A. So 1 upon A will make a transition to 2. Then 3 upon A will make a transition to, yeah, this is set containing 2 comma 4, 2 comma 4. And finally 5 upon A will make a transition to 2, which is still, I mean, it is not splitted yet. It should be written 2 comma 4, right? So if I observe this, no split required, no split. Okay. What about B? 1 upon B will make a transition to 4, which is part of 2 and 4. 1 3 comma B will make a transition to 4 again, which is a part of 2 and 4. And finally 5 upon B will make a transition to 4, which is a part of 2 and 4. So what can we conclude from this? From this we can conclude that 1, 3 and 5 make a transition to the same set, 2 comma 4. So there should not be a further split, right? Yeah. So at the end of step 2, now one more question is this: do we need to check for 6? So we need not have to check for 6, because 6 is a class that contains only a single state which cannot be further splitted up, right? So we need not have to check for 6. So at the end of step 2, my class's contents will be 2 and 4 getting splitted up, 2 comma 4, and 1 3 5 stays together, followed by 6. So the question is, do we need to continue with the step 3? Yes, of course, because we saw the split in our class content in step 2. So these are the contents of classes after step 2, right? So we have to follow with continue with step 3, because there was a split in step 2. Split, okay. Step 3, 2 and 4 cannot be further splitted, so I need not have to consider this, even 6, right? Now let us consider this 1 3 and 5. So 1 for A, let us check for A. So 1 upon A will make a transition to 2, right? And 3 upon A will make a transition to 2, and finally 5 upon A will make a transition to 2. So this clearly says that no split is required among 1, 3 and 5 with respect to A, right? No split. But there can be a further split among 1, 3 and 4 upon B. So we have to check for that also. So what is that? 1 upon B will make a transition to 4. 3 upon B will make a transition to 4 again. Okay. So lastly 5 upon B will make a transition to 4. Okay. So what does this indicate? This also indicates that no further splitting is required, since the transition happens to a same class, right, for 1, 3 and 5. So what I can conclude, no splitting required. So can I stop the iteration? Yes, because at the end of step 3 the class's contents are 2, 4, 1, 3, 5 and 6. So this is my content, right, at the end of step 3. Now if you observe, the classes content of the classes after step 3 is same as content of the classes after step 2, right? So which means that I need to stop my iteration and this is the minimum number. This is the minimum number of states what I get after performing the minimization of DFSM. Okay, so these are the states what I get. I need to stop my iteration. Now we have to write the transition diagram for the minimized DFSM what I got after step 3. Finally, we have to write the transition diagram for the minimized DFSM, and that depends on the number of classes what I got at the end of iteration. So how many classes do we have? We have 4 classes, right? So I'll be having 4 states in my minimized DFSM. And what will be the starting state? Starting state in my original DFA was 1, right? So a class that contains 1 should be my starting state in the minimized DFSM. So 1 is a part of 1, 3 and 5, right? So this will be marked as the starting state. Okay, and the accepting states are 2, because it was the accepting state in my original DFA, and 4. These two are my accepting state, and one more state will be 6, which is a non-accepting state. Now let me write the transition. 135 upon A will make a transition to 2, and upon B it will make a transition to 4. Similarly, 2 upon A will make a transition to 135, and 2 upon B will make a transition to 6. 2 upon B will make a transition to a class containing 6, and 4 upon A will make a transition to 6, and 4 upon B will make a transition to 135, and finally 6 upon A and B will make a transition to itself. It contains a self loop, right? So this is the answer for my minimized DFSM. Okay, so as you can very clearly see, the number of states in my minimized DFSM is equal to 4, and originally it was 6. So I have reduced the complexity of the solution by having a simpler DFSM. So this is my final answer. So these are the steps to be followed in constructing a minimized DFSM for the given problem. I'll see you in the next one.